Another common type of proof by induction question involves nth powers of matrices. So we can only find the nth power of a square matrix because only square matrices can be multiplied by themselves. And it turns out that there is in general a formula for a square matrix to the nth power, but it's quite complicated and involves use of eigenvalues and eigenvectors and so on. So it's too advanced for us to do now, but you can often guess what the nth power of a matrix is going to be. For example, if we'll take a fairly simple example. If we consider this matrix A, let's try and work out what the nth power is, just by guessing. So usually in a question, you'll be told what the formula is and then asked to prove it, but let's just have a go at trying to figure out what it is. So here we've got this times itself. So let's multiply this out. So first row and first column, we get 1. First row, second column, 0. First row, third column, 0. Second row, first column, we get 2. Then we get a 1. Then we get 0. And then we get 0, 0, 1. Okay? And then we'll work out a cubed. So that's a squared times a. So we're going to get 1, and then 0, 0, and then 3, and then 1, and then 0, and then 0, 0, 1. Any guesses yet as to what a to the n might be? You can work out more if you want, but you'll probably realize sooner or later that the nth power is just this matrix. So then the question is, prove this formula. So for n in Z+. So the proof, well, the base case is simply when n is 1. When n is 1, it is true. There's really nothing else to say because a to the 1 is a, which was given by this. So, and then we assume that the statement is true for n equals k. That is, we assume a to the k is 1, 0, k, 1, 0, 0, 0, 0, 1. And then we want to consider a to the k plus 1. So that's the same as a to the k a. And a to the k is this matrix, and a is this matrix. And then if we multiply these together, we get 1, 0, 0, k plus 1, 1, 0, 0, 0, 1, which is exactly what we wanted. It has k plus 1 in place of n. So therefore we can say the statement is true for n equals 1. And if it is true for n equals k, it is true for n equals k plus 1. So it's true for all n in the positive integers. And now we'll look at one that's slightly more difficult. So now, if we let M be the matrix cos theta minus sine theta, cos theta, we'll see this matrix later. So matrices can act on vectors. If we multiply this by some 2-by-1 vector, we could ask what the, so if V is V1, V2, we could ask what MV, which obviously we can work out what it is, but we could ask what kind of geometric effect it has on V1, V2. And we'll see later in chapter 7 that this is actually a rotation matrix. The effect this has is it rotates a vector by the angle theta anti-clockwise, centered at the origin. So the question is prove that m to the power n is cos n theta minus sine n theta cos n theta for n in n. So we'll prove this by induction on n. So the base case, n equals 1, is true. And there's really, not much else here to say about it. Sometimes you'll have something that's slightly less obvious. For example, if your formula was even more complicated than this, with several terms in each matrix entry, then you would have to write a bit down to check it. But here it's kind of just clear. And then we'll assume that it's true for n equals k. So that is, we're assuming m to the k is cos k theta minus sine k theta cos k theta. And then we'll look at m to the k plus 1, which is m to the k m, which is this matrix times m, and then we have a bit of work to do. So now we have to multiply these together. Remember, we're aiming for the same format as m to the k, but with k plus 1 in place of k everywhere. So let's multiply these out carefully. So top left entry is going to be first row, first column. So we get cos k theta minus sine k theta sine theta. And then top right entry is red row, blue column, which is minus sine theta cos k theta minus sine k theta cos theta. And then bottom row, so yellow row, red column, that's sine k theta cos theta plus cos k theta sine theta. And then yellow row, blue column is minus sine k theta sine theta plus cos k theta cos theta. And then we just need to think about the addition formulas. So in the top left, this is nothing more than cos k theta plus theta, which is cos k plus 1 theta. In the blue entry here in the top right is minus sine k theta plus theta, or sine k plus 1 theta. The bottom left entry is sine k theta plus theta, or sine k plus 1 lots of theta. And the bottom right is the same as the top left. And now we have what we wanted. We have all of these k plus 1s in the right place. So now we can make our conclusion. The statement, therefore, the statement is true for n equals 1. And if it is true for n equals k, it is true for n equals k plus 1. So is true for all positive integers n, or else for natural numbers, same thing. For all natural numbers n by induction. End of proof. Yeah, so matrix proofs, quite typically you'll be asked to find or to prove that a certain formula for the nth power of a matrix is true.